Hello, we are going to discuss about Wiener process or Brownian motion. So the year was 1900 when a French, in fact Belgian person called Louis Bachelier was working on the cotton prices in La Bourse of Paris. He identified that the cotton prices typically move in a random fashion, which is very similar to Brownian motion, which was identified in botany many years ago. However, later there was a gentleman called Professor Wiener who made mathematical calculations of these models and made mathematically possible, feasible and plausible models of Wiener distribution. Wiener processes are typically Markov. They follow fractals. They are IID in nature. That means they're independent and identically distributed. Interestingly, the Wiener processes, their increments are more important than the main process, and they are mean reverting in nature. So Wiener processes typically function as the base and fundamental of stochastic finance, empirical asset pricing, and financial risk management. Wiener processes are used on a daily basis regarding this. Stay tuned into this video for the properties and traits of Wiener process. Today we are going to now understand Wiener process, which is ideally called Brownian motion, but once Brownian motion was calculated and established, after that Professor Wiener made it perfectly suited for all stochastic markets, including the financial markets. And financial markets being stochastic markets, they follow Wiener process and we calibrate Wiener process. Today's video is all about the various characteristics and traits of Wiener process. So the first one of Wiener process, the characteristic is that Wiener process starts at 0. Wiener process at time 0, the Brownian motion is 0. At time 0, Brownian motion is 0. So it doesn't have an intercept. So intercept is the minimum value of y with all x's being 0. Here there is no minimum value, so no intercept is there. Now second, the Brownian motion BM or Wiener process we write with WT is, we write it like this, mathematical notation I am giving. Don't worry, I will make you understand. This capital N stands for normal distribution or Gaussian distribution. The 0 stands for mean and the T stands for variance. So the 0 stands for mean and this T stands for variance. And obviously this N stands for Gaussian distribution. Gaussian distribution. Okay. Now the increment is very important here. The increment, that is a third point. The increment of a Wiener process, that is WT minus WS, is also normal with the difference of 0 TS for S is greater than equal to 0 up to T. So basically, if the Wiener process starts at T and it goes up to S, then it changes values in between, and as it changes values in between, the incremental part of the Wiener process should also have all the characteristics of the major Wiener process or the main Wiener process. So every single part of Wiener process, every single increment has the same value of the major Wiener process. So what are the expected values? So let's learn the expected values. That is E of Wiener process WT is equals to 0. Therefore, we can write it like that expected value of WT minus WS is also 0 because it is martingale. Wiener process is martingale. And what about the variance? The variance of the var, WT is equal to T. Therefore, the variance calculation is WT minus WS is equals to T minus S. So it has got a steady variance, static variance. So increment of This Brownian motion or the Wiener process at time t minus s is normally distributed with mean 0 and variance t minus s. So mean is 0 and variance is t minus s for the increment. Now we will understand the fourth important point. This has to be stationary, completely stationary. Stationary means it is mean reverting. It is mean reverting. It reverts to the mean. So suppose if the mean is like this, the process goes up like this, comes back, again goes down, again comes back, again goes up like this. So everywhere you can see there is a tendency of coming back to the mean. There is a tendency of coming back to the mean. So this is the mean. So therefore it is called mean reverting process or stationary process with independent increments. The increments, so every time there is a delta, there is an increment, delta or these increments, these are independent increments. Okay, independent and they are identical. So they follow something called IID, independent and identical distribution. So the distributions of the increments are all independent and identical. Independent of each other and identical to each other. Okay. So example WT2 suppose minus WT1, this is having normal distribution with 0 mean and variance of T2 minus T1. This indicates constant variance and the variance here is T2 minus T1. So this is a constant variance. Also another important point is that this is a pure Markov process. Pure Markov process. That means it only depends on yesterday's value for tomorrow, rather today, and today's value for tomorrow. It's a pure Markov process. It's not a partially Markov process or it is absolutely 100% and it is a martingale. So Wiener process or WT is a pure martingale, not submartingale. You can see my martingale videos, not submartingale, not super martingale, but pure martingale, where just refer to my martingale video once please, it will help you to understand. So fundamentally a pure martingale video means the SO is equal to expected value of S1, where SO is the price of the stock today and S1 is the expected price of the stock tomorrow. Therefore it has to be a pure martingale. Another important thing here, for that I will shoot a separate video. I'm just giving you the concept here. It will be easy to understand that this is the 8th point actually. This entire Wiener process or Brownian motion, this is fractal. This is fractal. For fractal you see the fractal video, and then this is a continuous process and it is differentiable. So we can use differential calculus everywhere. It is differentiable. Is differentiable. So differentiable means you can take smaller bits and parts and deltas and increments and you can study the process, and that process will be exactly the same for the entire process. So it is a kind of a sampling you can do, subsampling you can do for a very short increment, but the same subsampling will work for the entire process. So this is a brief history of Markov process, and the last point here is Markov process follows Levy distribution. Levy distribution, it follows Levy distribution also, and it follows Levy jumps also, Levy flights also, and I will be shooting a different video that it follows Levy flights and what is Levy flights. So stay tuned for that video. That could be a nice continuation of Wiener process. Thank you very much. Stay tuned for the next video in the same series.